The presentation time is 30 minutes, including the Q&A session. Please welcome Neeraj and Manoj with applause.
Alrighty then. So how many of you have ever created a game or something, or have you ever wanted to have your Python games work on the browser? A few hands, I would say. Perfect. So yeah, so welcome to the session. This is playing games in the browser with WebAssembly, and we are Neeraj and Manoj, we're brothers. So today's agenda is going to be, so for today's agenda, it's going to be, we're going to talk about what exactly WebAssembly is. We're going to see the challenges we see in creating the apps on desktop and see how we can just like change them onto the browsers. We're going to go through some PyGames basics, and we're going to introduce you to Pigback or PyCheback, and we'll see like how we can convert those games to WebAssembly on the browser. And then if we have time, we'll just like have some Q&A. To begin with, how many of you knows or have ever heard about like WebAssembly? Perfect. So when it comes to like WebAssembly, there are like so many different definitions. Like when you talk to multiple people, the official doc or the definition goes something like, WebAssembly is a binary instruction format for a stack-based virtual machine designed as a portable target for high-performance web applications. So the main purpose is it enables high-performance web application can create those. It allows you to work on the web apart from just working with JavaScript, and it can run your code efficiently in your web browsers. And if you can see over here, the diagram says like not just the JavaScript can access those DOM or those web APIs. Eventually, any language can eventually be a part of that thing. So to understand this much better, like everyone is like working with Python. So this is how a Python execution flow works. So we start by creating a .py file, which is basically our starting point for creating any kind of Python program, which is a human readable code written by us. And the second step is like it's being compiled. So most of the people think like Python is completely interpretable language, but that's not the actual way of defining it. Python actually creates a Python bytecode, which most of you must have seen as like a PyCache file where you have like .pyc files available over there. So it creates a bytecode, which is not your machine code directly, but it's just the most closest thing a machine can understand. Then this bytecode is like saved in two ways. Either is it going to be for the modules, it's going to be .pyc, which is going to be stored as a cache. Why is it done? So that like the next time the computer is assigned the similar task, it can fast process this entire thing. Or it can keep those things in memory so that it doesn't have to do that and save and then go by instruction. It can simply execute it at the same time. And once this is done, these things are executive, and it's been passed to the Python virtual machine, which is a part of the Python interpreter, and reads and executes everything and eventually produces the program output. That's pretty much how Python works. And in a similar manner, we have WebAssembly. We write the code. It could be Python, it could be C, it could be C++, anything. It is being compiled to a WASM bytecode. So this bytecode is very similar to what we see in Python and all, and it's being stored in .wasm format. Over there, there's a key difference here. This WASM file is then stored into a WASM module, which is loaded and instantiated at runtime. It could be of the browser or the runtime environment which you're working with, and then it's been allocated to a linear memory. So WebAssembly uses this linear memory so that like every read and write task has to be done over there in real time, and then it's being executed and it's running. So it could be a C program running on the browser, it could be a Java program, it could be a Perl, Go, whatever you're working with. So behind the scene, most of these like interpreters are using OnScriptM, and we'll be seeing like one of those applications as well using Pyodide, and then we'll go to Pigback. And to understand more about like how exactly these things work with the browser, we saw like we have a source. It's being compiled to a Python, the WASM bytecode, and then it's being stored as a WASM file, and it's been instantiated at WASM runtime, but at the same time, it can also interact with JavaScript. So what does it mean? Is like, it doesn't even just like gonna be working with the code you're giving it to work with, only the Python one. It can eventually become a part of the JavaScript ecosystem and can access those web APIs happening on the browser. So what's happening is you give them an instruction, but at the same time, it can make use of the DOM and make those like fetch and all those like API requests at the same time. So that's how it works on the browser. It can manipulate the DOM. And one more thing is like it works in the sandbox environment. So even though whatever your code you're working with, if it's running on the browser, it doesn't get any other access than the environment it is working on. So it's much more safe and secure than your native applications you're working with. And yeah, then exactly the program is just like output and it's working on your browsers. Let's quickly see like what are the benefits of WebAssembly. The first one is like it's very high performance. It's not going to be slow. It's not exactly at the same speed, but it's like very close to your native web speed. And sometimes for some sort of computation, it's even much, much faster than your the JavaScript applications that you're running on the browsers. The second one is portability. It follows the principles of write one, run everywhere. So it can work on all major browsers, be it like Arc, Chrome, Safari, Firefox, whatever you're working with. Security, which we just discussed, it runs in the sandbox environment. So within the browser, it can't access anything outside of those things or any of those system resources. So it makes it like pretty much secure than the native plugins and extensions. And the last thing is like the interoperability, which is like it can work with JavaScript that eventually access the DOM, make those API requests. So we can use WASM for almost everything, but specifically for those heavy computational tasks like games, animations, or even machine learning, seeing some of those examples. So the next thing is like how we can create those synergies with Python. Like we know what WebAssembly is, we know Python is, we know how they're working. So how we can use them together and how exactly these things work. So the first thing which we just saw, Python code is converted to WebAssembly module, which is like one of the most crucial step to run your browser, which was previously impossible to do. Then it's being loaded in the browser from the Python code directly into the browsers. And the third thing is like your JavaScript interaction, which is happening, which we just saw because of the interoperability of the WebAssembly, which eventually creates the bridge between your connection. The fourth thing is the execution. So just like the Python runtime, WebAssembly also has the runtime, which is the port of CPython, which is Pyrodide, which you'll be seeing. It's executed within the WASM environment and allows Python code to run on your near native speed in the browsers. And then you can just like do whatever you're working with, from web applications to games to data visualization. But for this talk, we'll be focusing on how we can work with games. This is again one of those, another explanation is like you can have those WASM benefits, you can have those browser benefits, and you can have your Python features all together when you are combining all those things together. So you get those near native performance, you have a secure sandbox, but you can also work with, you can manipulate the DOM, you can have your API calls and everything, but at the same time, you can also make use of those Python-rich libraries or the scientific libraries or machine learning libraries what you're working with. And yeah, that brings us to the runtime we will be using for a few of those tasks, which is Pyrodide, which enables Python to run directly into your browsers. So the first question will be like, okay, what exactly is it and how does it like work? So the main few characteristics of Pyrodide is like, it allows Python code to run directly into your browser without a server. That's one thing. You don't need a server to run all those things. And it supports all the major scientific libraries already. So if you're already working with NumPy, Pandas, you can directly use them. It's built by compiling CPython to WebAssembly, and it brings the Python interpreter to the browsers. So if you see, there's a workflow diagram on the right-hand side, which says like the process starts with the JavaScript on the web, which is interacting with your Pyrodide. That could be triggered by the user action or the script running on the page. Then it's being compiled. The Pyrodide uses the Python interpreter that has been compiled into WebAssembly already. And it allows the Python code to then execute on the browser's environment. It also loads the external libraries if you want to import something like NumPy, which is already there, but like this is how it also load those packages. And it also executes them within the WebAssembly compiled Python interpreter, and then it returns the results coming back from there. So overall, it uses the foreign function interface to JavaScript, which allows the JavaScript to directly make those API calls. A very basic intro to like how Pyodide works is we can make use of those JS modules for Pyodide. So the line let Pyodide equals to await load Pyodide initializes the Pyodide environment asynchronously, which is very important. We don't want to get stuck or get hang up. So this loads the Python environment in the browser, setting the stage for the Python experience. Then we have a very simple execution, which is pyodide.run Python, which is just like logging the printing the hello world statement, which will demonstrate like how, or we can say like, which will demonstrate that the Python environment is running on the browser now. We can load those packages by, let's say if you want to load NumPy, we simply call pyodide.load package NumPy, which shows how to load additional Python packages. And similarly, we have those JavaScript interactions and all. So to quickly go to the next one, which is, okay, so now what you're gonna do is like, we're gonna quickly see an example, and I'll also give you a quick demo on Pyodide, which is the init Pyodide function is defined as an asynchronous function. So it uses await to initialize the Python environment. There's a simple execution happening, which is because of the Pyodide run Python, again, the same thing. And we execute those functions by defining a square function, which is returning just a square number, and everything is being handled. And eventually, we just like call the init Pyodide function. So this is like a very basic example of how you can create a function in JavaScript and call the Python function under it, and it can just like run it live in a browser. We can similarly make use of those external libraries like NumPy. We similarly do the same thing. We make the runtime work like run Python async, which is deprecated kind of, but you can still use it. And we can make use of the NumPy arrays, make the mean of it, and create the standard deviation. It will just like log out everything you're just like working with. And here is like a simple example, which is we have a JavaScript function which is embedded under the script tag within the HTML body. Then we have the same Pyodide setup, which first creates the Pyodide environment, then loads the NumPy package. Then we have a Python execution. It then runs, if you see over here, it then runs a Python script which uses NumPy to generate a random 3x3 matrix and then calculates a determinant. And we will also have a trigger mechanism, which we initially discussed. By clicking a button, this entire process will be triggered. And this is how it works, which we just discussed. And so after this session, you can also access like a code repository where we all have all these kind of like files and all. So this is called index.html. If you can go up here, okay. Okay, I also have like maybe at the end of the talk, I'll just like give you the demo. I'll just have to open it. But if you will have like a user interface, you click on that function, and that function will just like run those matrix multiplication calculations and give you the output on your browser itself. So because we don't have a lot of time, so Manoj is quickly gonna begin the part on Pygame, and then we'll see like how we can make use of Pygame, and then how we can use PyGN to convert your Pygames and make them run on your browser without even using or running the Pygame locally.
All right, so any gamers in the house here? Somebody playing games or writing games by yourself? So Pygame is a module written in Python more than like 20 years ago, and it does quite surprisingly a lot of things under the hood. So if you have been using or understanding computer graphics, which is the fundamentals of how games work in general, Pygame is basically a port of like the Python API to access and play with those like SDL modules. So, just a moment.
We're on the wrong.
Okay. So Pygame is a Python wrapper for the SDL library, which stands for Simple Direct Media Layer. It allows you to write cross-platform, like from Python modules designed for writing video games, includes the computer graphics, the sound, images, whatever you want to include in your games. And it uses SDL. I think now it's like SDL 2.0. And the cross-platform nature of both the SDL and Pygame means that you can write games and rich multimedia applications using Python, and it supports like every platform. So let's move forward. It does like 4 very important things: graphics rendering, sound handling, inputs, and the main part is the game loop, which basically processes the user input. It updates the state of all the game objects, then it updates the display and the audio outputs, and also maintains the speed of the game. How does it work? We're gonna go in step by step. So how does Pygame works? So you import Pygame, you initialize, and you allow Pygame to connect its abstraction to the specific hardware, be it like Windows, Mac, whatever device you're using. And this function calls a separate init function of all the included Pygame modules. And since these modules are abstractions for specific hardware, this initialization step is required so that you can work with the same code, be it Linux, be it Windows or Mac. And finally, you need something drawn. So you need a display object, or like your draw board, let's say. And finally, you have your main game loop, where you run a infinitely running loop until it ends at some point. And in that meantime, in that loop, you update the objects, you render the graphics, and whatever processing you want your game to make. All these code examples are in the repository at the end of the time. We'll share with you as well. And the third thing is like the event handling. So Pygame captures events like key presses, mouse clicks, whatever like interactions that you want the user to do using an event queue. And as a developer, we can process these inputs, these events to control the logic of the game. And this happens within an infinite loop. And finally, we do some rendering as well. If you want to draw some shapes, update the objects, put some background images, and these are called during the game loop to update the display. Going back into the syntax, so initially we started with importing the Pygame. We initialize all the required modules. We call the init method. Then we set our mode, and you can have captions. We can have background set up at the beginning of our game. And then we load the images and sounds, so you can have whatever like background music playing as the game loads, or even the duration of the game. And you can start these at the beginning of your program. And then you run like an infinite loop, which handles all the events and updating displays. So you check for events in the game wherever there's like a keyboard or mouse action, and finally you show them. So you flip it, and I'm going to show you like what does that mean exactly. So there's an example where we set up the game window by initializing, putting like a display, like a 600 by 600 box, and we set up the response, the surface, and then we create the game loop. And this game loop is the core of any game that you write in Pygame. So it detects and processes user inputs like keyboard presses, as we discussed, and finally we update the window basically. And so this code is actually part of the game. So it checks for the user input to close the game, updates the game state and player position, and clears the screen and exit the loop, and closes the Pygame when quit is detected, which is basically like if there's a click on the game window in our case. And you can add movements, and these movements are made for moving like a box, like left and right, and you can do it with your keyboard. This code is part of the bigger file that we have used for this. Very important thing is to blit or to flip. So Pygame by default uses like a computer graphic concept called double buffering, which is used to prevent flickering, so that you can put everything to a buffer, and then at once you can put it to the display, so that your monitor actually renders like everything at once, instead of flickering and like all the objects coming like at different times. So we keep blitting, and then at the end, like we flip like every once we want to like update the game or the position of the sprite or the object that is within the game. And then Other important thing is collisions. Like how do you detect collisions? Very common strategies. There's like some typo there. But one of the most common collision strategy is the axis aligned bounding box, which is how you have like different like boxes. This is in 2D. There's also in 3D as well. And you detect like if they are like either hitting together or actually like overlapping. There are like more. You can also do like circle, hash maps. And the most expensive is the pixel perfect, where you actually match if there's like a pixel like colliding. And there are more like strategies for detecting collisions. But basically, understanding that you have a surface to play with, you have certain objects that you can draw on your board and then on your game. You can move them around and you can detect collisions. You can have different objects like sprites, which are also like more like in depth of the Pygame like module. You can take a look into it. But this is the fundamental like understanding of like how Pygame basically works. So for this as well, like there's a file called snip4 in the repository, and this works like here. So it just like moves around. It's a very simple program. And the moment like it hits, in Pygame there's a method called like collide rectangle. So you use that to figure out if there's a collision happening, and then the game is over. Basically, you put it on the screen. And yeah, so another tool for packaging Python games, especially for web browsers, is PyGBag. I don't know how to pronounce it, like PyGBag. Neeraj is gonna tell more.
Perfect. So before that, we can also see like how exactly that snip4 thing is working, and then we'll see. I hope you guys are able to see that. Nope. Can you see like a game window being opened? Oh no. It's gonna be here. Okay, now I think you guys should be able to see it. So this is going to be the fundamental for the next topics on the PyGBag. So just like the objects we're using and moving them on the screen, and once they touch, the collision happen and the game is over. So the problem is like this is happening on your desktop. It's not working on the browser, and now the task is like how we can just like convert this and make them work on the browsers. So if we just like close this up, go back to the presentation. So we have something called PyGBag, which is helps you run those Python applications or the Pygame applications on your browsers. So how PyGBag works, how PyGBag works, my bad, not PyGBag. How PyGBag works is like it bridges the gap between the game development and the web development thing, and allows you to create one app and then run natively on your browsers and your desktop at the same time. So it has three basic functionalities. One is compilation. It uses OnScriptum to compile those Python applications and convert them into WebAssembly. And it has asset management. What does it mean? It's like it creates the virtual file system on the browser for every single runtime which is happening. And it makes like an asynchronous adaptation, which is it implements an asynchronous event loop. I think most of the people who already work with JavaScript must know like how those event loops works in the browser. And it converts your Python synchronous way of doing this to an event-driven environment on your browser. So the next thing is like, we have a few other things, like it's the same thing but in depth, but we don't have time to go everything. But just like packaging tool works, then it works as a code translation, converts your code to WebAssembly, does the asset packaging, does your web wrapper creation, creates your HTML and all those things, all those outputs from your Pygame inputs. So the important thing is like how we adapt from Pygame to PyGBag. So the first thing is like we have to replace those display.update function to display.flip, which Manoj already talked about. The one key principle is because of update is way slower when it goes to like web context, and flip swaps your entire displays, and it's often very fast and reliable in those web environments. The second thing is your asynchronous main loop, which says like use an asynchronous function as the main function on your browser, and it why we need this? Because web browsers uses a single-threaded architecture, which is like an event-driven model, and the page can become unresponsive or a black screen can happen on your screen. So you need to use an asynchronous way to run your Pi games on the browser. And the third thing is like event handling, which ensures like no other, just like handles the non-blocking thing. It should not pause the game loop momentarily, and it should allow like the background task work at the same time something is happening on your screen on the browser. So the example we'll be building in this demo is a same principle, but we're gonna create a snake game. I think almost everyone must have played that snake, just like finding the food and just like growing on your phones, like old button phones. You guys must have played that game. So to quickly go through what we're doing is we create a main game loop, which is defined as an asynchronous function, which you just saw. And we also pass an async IO, the async IO.sleep 0, which is used to yield control back to the browser. Otherwise, it will become just like unresponsive. And we just like call the function main to start the game. And just like that, a rectangle will be created on your screen. So using the same principle, we move forward. And this is exactly how your entire architecture for Pickback works. We use Pygame as the starting point, which is your original Python code which is using Pygame. And then Pickback is like the Pygame package manager, which is the main tool orchestrating your entire process, which is using OnScriptIm as the key component, which is used by Pickback. And you can say it's like a toolkit which converts your, compiles your C, C++ to your WebAssembly. And the same thing we just saw, like which uses a JavaScript code, which use the package assets, creates those HTML and JS generation wrappers, and eventually run those things in your browser. So to end this, we will see like how we can create those snake games. We initialize the application or the game. We set up the game environment. It imports the modules and initializes the Pygame, create the game window over here. And then we have included the async IO or the async function, which is very crucial for the Pickback compatibility, and which will enable the game to run in your web browser. So all the game initialization has happened here. Then we have a main game loop structure, which is like the code for your anything game which you are creating on a browser using Pygame. And it creates like an event, asynchronous event loop that continuously updates the game state again and again and handle events and renews the screen so that like the screen is again not just like blocked or paused for like a longer time. And yeah, the same thing, the async IO.sleep 0, we're getting back the order which is essential for deployment. The same purpose, we want the browser to be responsive at all times by yielding control back on regular periods. Then we have the event handling and managing those snake movements and this specific piece of code. And one more thing, this is not the entire code. We'll give you the repository. This is just like giving you the more or less the structure of how things are working. And this specific piece of code just like manages the user input and the snake movements. It checks for like key presses, which you can see, and just like changes the snake directions and updates the snake position accordingly. And this is eventually demonstrating how the user will interact and update the game object positions in real time. And this is the same thing which Manoj told you about, the collision detection. And this snippet implements the game rules, basically. It checks for if the collision has happened to the wall or it has happened to the food. If it hasn't happened to the food, we'll just like make it grow. If it happened to the wall, we'll just like break the loop and your game is over. And then we have like specific draw functions, which draws the grids, the snakes, the food, and demonstrates how your Pygame's drawing capabilities work and how you can create those visual elements onto the screen. And yeah, the last thing is like you just like run that like as an entry point of an asynchronous main function and just like deploy it. So how this thing works on the browser is if I, instead of the same game, if I run it on browser, I can say, okay, really sorry for this. I think you're not able to see my command line, but like if I just say Pickback and the name of the folder of the game and run the same thing on the browser using, it's gonna run on localhost 8000. So it's gonna take it's going to take a while. Well, it just like downloads all those packages, converts them into WebAssembly, and then once you say, okay, I'm just like ready to begin, you can just like anything which any game you're just like creating on the browser will just like, on your desktop application will now run on your browser. So you don't have to change anything specifically. Everything is done by PyGMG directly, but yeah, this is how your game has been created, and once it just like reaches the wall, the game is over. Yeah, that's the video for the same, and yeah, thank you so much for joining, and this is the end of the talk. I think the screen is somehow stuck now. Oh, no. So we're on the wrong page. So yeah, thank you so much for joining, and this is how you create your games in Python, and natively you can run them on your web browsers using WebAssembly or using the computational power of WASM. And yeah, if you have any questions, let me know. I'm happy to answer most of them.
Thank you so much for the presentation. And if anyone has any question, please raise your hand.
Hello. I wonder what's your motivation to convert Python code to WebAssembly running on the web browser? Did you want to have a cross-platform game? Or if the target is only on the website, why did you choose to use Python to write WebAssembly? Because WebAssembly is supposed to, usually we're supposed to use C++, C, or Rust because you use LLVM to compile, right? Using Python is obviously not a ideal option. So, yeah, I'm just curious about why did you choose to do like this?
Right, so the main purpose for the tutorial is like, it's one of those applications you can use if you're already working with like a lot of these like Pygame applications. I have been working with graphics or games being created in Python. This is one of the opportunity for you to adapt to that WebAssembly environment and grow further and just like take those games or graphics from your desktop applications to the browsers. But yeah, this is just an application. Definitely, it's up to the user who's just like creating those games. If you're not coming from the Python background, if you're directly working with some browser application, you don't have to use Python. You can just like go with the JavaScript and just work with the DOM and all, just like make some games, work with the graphics. But yeah, this is one of those applications. If you're already a Python developer, you're working with a lot of these graphics and games, this is one of those possibilities where you can bring those computational power of Python for creating those games using Pygame and just put it on browser now.
Yes. I also wonder, so once you convert Python code to WebAssembly, how did you deal with the website UI? Because I think WebAssembly doesn't support to operate the HTML.
So you don't, so it's not gonna change any of your UI. Every UI which you're just like creating is gonna be a part of your Python code itself. So every game we are creating is a part of your Pygame. So every UI, every graphic is something you have written in Pygame itself. So the only thing the WebAssembly is doing is just like taking it and just like making it run on the browser. Nothing is being changed by it on the browser. Similarly, if you're working with Python and all, you just like create a UI using your JavaScript or your HTML and everything, and the only piece of thing which is being used by Python is like it just like calls the JavaScript functions and then make your function run in the browser at the same time.
Okay, I got it. Thanks.
Does anyone have questions?
So thank you for a good talk. I specifically liked your, the slides, if you can call them that. But I wonder, when you run the game in the browser, what happens if you resize the window, as people do, like if you use it on different kinds of resolutions or mobiles, or How does it deal with that?
So again, it's a part of the Pi game. So we're not specifying anything on the side of the WebAssembly. So the game window and everything which has already been specified on the Pi game will stay the same. I think it's a very similar question. So if you want to have that resizable images, you specify that in Pi game, and the same functionality will work in the browser itself.
Okay.
But yeah, if you see like the window size was like a little smaller, and that was the actual window size which was put up on the browser itself, we saw like those padding coming on the screen.
Yeah.
It's not gonna automatically resize those images or just like reduce those sizes, because it's gonna be eventually like a coordinate system, like a 2D Cartesian plane. It's always gonna be your pixels you are just like specifying.
Got it. Thank you.
Here.
Hi, thanks for your talk. I really liked your animations in your slide too. They're super cute. I'm curious about what the debugging story is like. Like what happens when your game crashes in the browser? Am I going to be debugging JavaScript or
so PicBag also provides you with a inbuilt debugging, like a UI, where you can directly get like all the debugging logs and everything directly. You just have to go to the link where your application is running /#debug, and you can debug everything. So yeah, and you can also like debug those things at the same time. You will see like the changes happening. You can see on the top right button, top right side of the section. So yeah, it provides you that debugging capabilities out of the box.
Cool, thanks.
Alrighty then, thank you so much for joining. Yeah, have a good one.